Good afternoon, everybody. I am going to talk you about the biological grounded mean field model of the cerebellum that I'm working on. Okay, let's start. Our brain is made of several interconnected networks that contribute to its global activity. Cerebellum is among these networks, and a lot of modeling approaches have been developed during the last year in order to investigate the role of local networks in the brain dynamics. But the cerebellum specific model is still missing, even though cerebellar circuitry is very, very peculiar and markedly different from the cerebral cortex ones. So in this background, we aim to develop an advanced mean field model of the cerebellum in order to have a deep insight on its network functioning, but also to be integrated in whole brain dynamics simulators that already exist. Okay, I will show you our pipeline that starts with the network design starting from a scaffold model. This network is our generative model for the mean field formalism that we used to model the cerebellum activity. The core of our mean field is the transfer function that has the role to translate the input for each population in an output. We implement this pipeline in Python 3, and we compute a semi-analytical form of the transfer function by a double-step parameters fitting. Okay, let's have a look to our network design. The population we consider are the granular cell, the Golgi cells, the molecular layer interneuron, and the Purkinje cell. We keep the topological organization of the population, and our functional reference is the Edge-Elite single-point neuron equation. Detailed scaffold model have been used to set the connection probability amongst this population, and the same is performed for the quantal synaptic conductance. All these features are collapsed in the equation of population-specific conductance. Here we can see an example for the molecular interneuron where the excitatory input is specific for MLI that's coming from granular cells, and the inhibitory is the autoinhibition of the MLI, so it will be different from the one of Golgi, the one of granular, and the one of Purkinje. All our features that are really adherent with biology and physiology of the cerebellum are used to compute the membrane fluctuations properties that are the average, the standard deviation, and the autocorrelation time of the membrane potential. And here we can see an example for the Purkinje cells where, for example, the mean average voltage is computed starting from the specific population conductances of MLI and granular. Then, once we have computed the membrane fluctuation properties with a double fitting procedure, we arrive to a semi-analytical transfer function expression. Our pipeline is implemented in Python 3 in order to be more flexible and to be integrated in an already validated framework as the virtual brain. And here we can see that the first step is to compute a transfer function numerical template that is generated from our network, and it is the reference for the optimization of the transfer function semi-analytical expression. For example, here we can see the example for the Purkinje cells, and we can see how the granular and MLI conductances are used to compute the fluctuation properties of PC and then the transfer function. Okay, so this is our network with all the biological and physiological features that are translated in the advanced mean field model. The word advanced coming from the fact that we have an equation like this one, a first order dynamic equation, specific for each population for a transfer function specifically fitted, taking into account the connection properties and also, for example, the quantal conductance and the population conductance specific for each population. Furthermore, we have two further equations for the adaptation. The first one is for PC, and the second one is for the Golgi cells, in order to keep a strong adherence with the biology. Okay, I would like to thank you for your attention, and I still just 1 second more for a special acknowledgement for my co-authors, Alice Geminiani, Claudia Gandini, Fulvia Palesi, Claudia Casellato, and Egidio D'Angelo. Now I think it's time for questions, so I'll be very happy to answer to all of your questions.